Expire-Span scaling transformer by forgetting, reducing computational costs by differentiably dropping memorized embeddings from self-attention context. Okay, so this is a paper about scaling of transformers, especially autoregressive ones. And before going into the details, I will go through the recapitulation of the self-attention, which is the core part of the transformers. So transformers input is a sequence of embeddings of dimension d and length L, and the output has the same dimension, same shape. So once we have the input, in simplified terms, in the encoder, what we do is just take the input, create three matrices by linearly projecting the input with some weight matrices. And these three different sequences are then called query, key, and value. What we do with them is that now we do sort of soft sequence-wise nearest neighbor search. So we effectively search keys, search queries as a sequences of embeddings in the keys, and where we find match, we output more of the corresponding value in that position of the sequence. So for all L times L combinations of the sequence elements from keys embeddings and queries embedding sequences, we find for output position M the maximum of the correspondence between key and query and output value corresponding to the most matching key. So we do this sort of key value search, and that's the core. We can describe it in the pseudocode in following way. So we first do effectively dot products between our key values and queries, and we do that in the dimension d of the embeddings. Then we perform softmax in one of the one of the sequence dimensions. So we find the biggest match between keys and queries, and for the biggest match on that position, we output corresponding value more. That is, we weight by softmax of the dot products. Can as well, in simplified terms, describe it as softmax of query times k transposed times v. You can read more details, and attention is all you need paper. There also have these visualizations that we have this query key and value input. We do this matrix multiplication, that there's some additional scaling, but important is the softmax here. And then once we apply the softmax, we do matrix multiplication back into the values. What's important here is in what dimensions we do what. The issue with self-attention is the complexity, which is quadratic in the sequence length. So for long sequences, we need to do quadratic amount of computations. That's because of the softmax, because of that each comparisons. Problem is that the context size is actually crucial for some of the tasks, right? For example, for character level models, where for each characters we have some embedding, and if we want to have reasonable amount of text in the context, it needs to be quite a lot of characters, and that gives us huge complexity. So how can we speed this up? There are multiple approaches. So for example, there's an approach called Performer. I actually have post on that. You can see that post and video. It effectively what it does is that it breaks down construction of this attention matrix, which is L times L, into creation of multiplication of two matrices which in between have lower dimension. Super interesting. I really like that one. And what's the next? So the next thing is, next was the big bird. So that one, instead of calculating attention for all inputs, it sort of collected only sparse attention, right? So only for some of the queries and keys it actually became part of the attention, and then the attention was calculated. And yeah, there are other approaches. For example, if you have autoregressive problem, you can use this sort of sliding window, or in general, even like instead of just using some sort of sparsity, we do this sliding span, that we attend only those words that are not that far from each other, and we attend only those combinations of words. And long former is sort of a combination, uses sliding window, sparse, and in certain places attention on those positions all the times. So let's go into the autoregressive transformers. That basically autoregression means that from previous we predict the next, and for this we use one directional attention, which means that we only match those keys, and we only match queries from the future to the keys in the past. So when we do the attention, we only attend towards the past. So it's sort of one direction attention. It's called. It's very useful for language modeling, because if we want to predict the next token, we can only look into the past in each step. So it makes sense to have also one directional attention. And all models that I will describe below are autoregressive. So transformer XL, that was a paper preceding Expire-Span paper. It's an abbreviation for extra long. Alright, so what it does, it instead of recalculating everything in the sliding window every time, it keeps some memory, which means that it loses some of the gradients, but at the same time it sort of simulates wider attention context. How does this work? So for example, here is a sequence, here are layers, and for example, this dot above x3 attends to position x2. If we have this context. So in the context, I have x2, x3, x4, x5. If I move the attention context with the sliding window towards the right, suddenly the x3 cannot attend to x2 if I recalculate everything. But instead, I can remember the output here from the previous step, and then suddenly it works a little bit as if I focused also on x2. However, I may lose some of the I will lose some of the gradients. So I memorize previous results instead of recalculating. That increases context, but I need to be careful. There is also thing positional embedding, some of you know, and I need to make sure that those are relative, because positions between the inputs are also important, and in this case, it's super important that those are relative. What is compressive transformer? So compressive transformer, instead of using it still uses sliding window, but it also remembers past, and it remembers past such that it still have again even sliding window for sort of long-term past, but it compresses multiple fixed amount of tokens into some sort of compressed memory. The issue here, so it has some additional function which transforms, for example, three last tokens that are about to drop from the context, and it produces one compressed token, one compressed embedding. There's a flexibility issue that you can only map fixed amount of this compression window is fixed size, so only three tokens will become one. There's maybe there's lack of weighting, what should I compress more, what less, and as well because compressed memory is still fixed size. Then there's adaptive span, which is a model which adaptively increases context length as needed. So if it notices, okay, at the beginning here there was this important part of the text, so it's able then to suddenly start expanding the context, and always making sure that the beginning of the text is in the context and I can compute the classification. It's similar to Expire-Span, except it learns to increase span length instead of remembering specific tokens. So now we are getting to the Expire-Span attention paper. It's a Facebook paper. Not all memories are created equal. Learning to forget by expiring. It has also source code available in PyTorch. It uses as well the memory allowed transformer XL, so it sort of never recalculates tokens that were already calculated, and there's some sort of minimal span, sort of minimal window that's always available. It has some kind of maximum window where the tokens can be added into. And it does this extra trick that it has additional function that predicts, how when I am calculating this new token, in each new step, I would like to say, how long I would like to keep memory of this token in my RAM, right, or GPU memory. So in this way, it can selectively forget certain embeddings, certain parts of the sequence in the corresponding layer. So in each layer, it does this, in each layer of the transformer. It can selectively forget tokens in this way. It can learn to forget, learn to remember what is important. Once the model slides over the time steps and the memories in the context sort of fade away. So what does it mean to fade away? So the attention matrix output itself is scaled by the amount of by how much the token is still remembered. So the token is predicted, okay, it will be remembered for this time, and then over time its sort of memory expires, and its weight in the attention matrix goes down in this way. What it means, that we can differentiably we can get a differentiability in this memorization as well. What is the effect of forgetting tokens? Well, the most important part is that we again compress the amount of tokens on which we calculate the attention, and that's why it's important. We save the memory, we save computation, we reduce the computational complexity. The loss for Expire-Span has to be modified a little bit. We need to make sure that the model is trying to keep only what's important. So we penalize it linearly with number of memories that it keeps. We add to the loss function additional term, which is the sum of the memory weights that it keeps. Also, that they do additional regularization for shortening the memory. Of course, you have an extra parameter alpha, which is a compression parameter, which in the loss function, which tells you where you can configure how important it is for you to keep the memory. And yes, these parameters, there will be more of these hyperparameters in this model. So this model outperformed on English Wikipedia 8 compared to similar models. So compared to Transformer XL, Compressive Transformer, compressive to the adaptive span, the Expire-Span had better performance, required less GPU memory, and time per batch was lower. What is actually this metrics? Bits per byte. That's language modeling metric. It's basically average of negative log base 2 probability of predicting the target label. You can as well inspect in what the model remembers. So once it is reading text, it, for example, remembers characters from the word Egypt here, characters from word Alexander, while as it does not remember non-specific words like somewhere. Alright, so I think there's one more comparison with all attention. So this Expire-Span has more parameters, about the double, if I understand this table correctly. It has double number of parameters, but it has better performance. Alright, that's it. See you next time.